Hello, my name is Matthew Harrison. I'm a farming systems scientist at the University of Tasmania in Australia. Today I'll be talking about soil carbon markets, whether it's science or snake oil. I recently did this presentation by invitation to a large international bank. Why all the hype about soil carbon? In Australia, we've seen, in particular in the last couple of years, a high level of interest in soil carbon and soil carbon markets. Ross Garnaut, a preeminent Australian scientist, said that Australia can make an exceptional contribution to its climate action by creating natural systems that store more carbon in soils. We had what was called the low emissions technology statement, which suggests that we could increase soil carbon and reduce our national greenhouse gas emissions by up to 16%. We then had in late 2021 what's called the Clean Energy Regulator, and that's the national body for producing greenhouse gas emissions policies. So that reduced what was called the Soil Carbon Emissions Reduction Fund, or ERF policy, that allows Australian landholders to be paid for improving their soil carbon. And the Clean Energy Regulator also provided incentives to landholders to do that, so up to $5,000 cash back to support soil carbon baselining. Then early in March 2022, we had the government at the time announce what was called the National Carbon Challenge to reduce the cost of measuring soil carbon down to $3 per hectare. And you might say, well, what's the current cost of measuring soil carbon? Well, the current cost of measuring soil carbon, I did some talking around to some providers, and I found that it varies quite widely. So some providers, for example, $40,000 for 1,000 hectares, and that's every 5 years, and you have to do it for a minimum of 25 years, so that's 200,000 Australian dollars. Other ones were significantly less, but they actually took a cut of your carbon credits earned as by way of a non-cash loan. So the actual cost of soil carbon sampling varies widely between providers. So based on my anecdotal sample, it's between $30 and $175 per core, noting that you need a minimum of 9 samples for the 2021 soil carbon policy, or soil carbon ERF in Australia. Now that can be paid in what's called ACCUs, or Australian Carbon Credit Units, which are basically one ACCU is 1 tonne of CO2 equivalents per hectare, or 1 tonne of CO2 equivalent, sorry. So it can be, your actual costs of sampling can be paid in ACCUs as they're earned, which is a type of loan, and that ranges between providers. It can be between 15 and 30% of your carbon credits earned is paid to the provider. So it ranges quite widely. So in my estimation, the total cost of sampling soil carbon ranges from about $15 a hectare to $60 a hectare. So the national government's aspiration to get it down to $3 a hectare might be a stretch goal, but any research and development in that direction that reduces the cost through, for example, remote sensing or process-based modelling will be useful. Now, what sort of returns do you get when you make an intervention to improve soil carbon? Well, it very much depends on where you are, the initial soil carbon, the history of the place, the soil type, the climate, and a whole bunch of other factors that I'll talk about shortly. The range is the change in soil carbon, I've got 0 there, but it can be negative, can be up to 0.8 tonnes of carbon per hectare per year or more, although that's probably a stretch target. So soil carbon returns in Australia between 0 and $24 per hectare per year. Anecdotal evidence suggests a large range in returns at the farm scale, so negative 250,000 up to $2 million gain, so quite a wide variation. But one thing I would say, and we've shown this time and time again, that at current carbon prices, well, at least at carbon prices of $20 a tonne of CO2 equivalents, or $20 per ACCU, the income from productivity of improved soil carbon is worth much more than the carbon income per se, and that's due to things like additional nitrogen mineralisation, which can be $120 to $200 per hectare per year, and I've got some references there. But at those carbon prices, the improved productivity associated with improved soil organic matter is much higher than the income of carbon per se. And if you just look at the carbon returns between $0 and $24 per hectare, that range is somewhat lower than $15 to $60 a hectare, which is the cost. So I'll talk about other ways to make income from carbon, including productivity, later on in this presentation. But first of all, what do soil carbon budgets actually look like? People are probably familiar with the soil carbon cycle, but what about the actual soil carbon budget? Well, soil carbon is the largest carbon pool on Earth, so a small increase in the carbon in the soil will result in a large change to carbon circulating in the atmosphere, and I had on that initial slide up to 16% reduction in Australian national emissions. Australia is a large continent though. Now, microbial biomass adds about the same amount that's lost in respiration each year. So it's constantly cycling. It's getting fixed, it's getting sequestered and being added to the soil, and it's actually being lost. Carbon is always cycling. So if we want to improve carbon in the soil, we have to increase the rate of carbon going into the soil relative to that being lost. Now, it's somewhat difficult to reduce the amount being lost because it mainly depends on soil temperature, but to a large extent cultivation. So if you cut out that, you'll reduce that respiration thing. But probably the main way to improve it is to increase that flux of carbon going into the soil. But measuring soil carbon stocks statistically, or measuring change in soil carbon stocks over time, is very difficult. So if you look at these numbers here, we're talking about a net sequestration number per year of 3 relative to 2,500. So at the time of speaking, our ability to measure the change in soil organic carbon often has a higher error than the change that could occur in a few years. So there's a lot of research underway to statistically validate change in soil carbon relative to that large mass that's there now, because soil carbon varies from point to point and depth and soil type and all over the place. There are other ways to store carbon in the soil, and they're typically engineering ways. So you can capture, it can be a point scale source where you actually capture concentrated CO2 coming out of a power plant. It can be direct air capture. It can be bioenergy with carbon capture and storage. That's called BECCS. You typically grab that carbon and you can pump it between 1 and 2 kilometres down below the surface into, for example, a depleted oil reserve, and that can force out methane that's actually in that gas reserve. So it can have a lot of benefit, but that's very expensive. You're talking about a multi-million-dollar exercise, and arguably is the reverse of fossil fuel burning, which is digging out these carbon reserves and burning it and circulating in the atmosphere. And I would argue perhaps a lot more effective than storing carbon in the surface of the soils, which can be easily lost again. That said, I won't talk about this engineering method any further in the presentation, but it's worth noting that it exists. Now, there's 5 main messages that I want to talk about in the presentation, and the first is that soil carbon markets tend to focus on what's called permanence, but short-term carbon offers the greatest fertility benefits. So what do I mean by that? Well, there's typically 3 pools that soil scientists talk about. The first one is the labile pool, and that's cycling very quickly. So that's fresh residues and living organisms, and only really lasts up to 5 years in the soil. Then you've got the second one, which is resistant residues or physically protected, and that can last up to 40 years in the soil. So that's called humus organic carbon, or HOC is the abbreviation. Then you've got resistant organic carbon, or recalcitrant carbon, or even charcoal, and that's very much protected, and that can last thousands of years in the soil. Carbon markets tend to focus on what's called permanence, i.e. permanently out of the atmosphere. In Australia, our ERF, or our soil carbon policy, talks about periods of 25 to 100 years. Now, resistant organic carbon, or recalcitrant organic carbon, lasts the longest, but doesn't have a lot of value in terms of soil fertility and plant growth. Think about charcoal on your garden, probably won't do much. Then you've got particulate organic carbon and humus, have much greater value in terms of fertility, but they degrade a lot quicker. So in the short term, interventions or any practice changes you make to the soil mainly change particulate organic carbon, to a lesser extent humus, but particulate organic carbon is really easily lost. So if we're talking about permanence, particulate organic carbon must be continually added as older particulate organic carbon degrades, and that particulate organic carbon must be maintained for a minimum period according to the soil carbon policy, or the ERF, of 25 or 100 years. Now, the more that you cultivate, typically, this is a stylized diagram, so it's obviously it's smoother than what it would be in practice. The greater the cultivation period, the greater the reduction in soil organic carbon in tonnes per hectare. Now, If you had some arbitrary point in time where you had land use clearing, so for example you had vegetation, in Australia that might be the 1860s or the 1880s, you clear that vegetation and then your total soil organic carbon is gradually tending downwards, and it's probably a little bit staggered due to cultivation, for example. And then if you make some permanent change, say 30 or 40 years after that transition to a permanent pasture where you cut out cultivation, then what will happen is that you'll see soil organic carbon increase. Probably the point to make, though, is that for the same organic carbon, you can have very different fractionations of carbon. So this one's only got 8% particulate organic matter. After the intervention was made, you can see this yellow fraction. Particulate organic carbon's gone up significantly. The second main thing is that the resistant organic carbon, like the charcoal fraction, hasn't changed. It's still the same. It's this brown fraction here. So it's very difficult to change in the absence of, for example, fire deposition or biochar spreading, which is an external amendment, actual intervention that you make to the soil in the absence of fire, and which fire can lose a lot of carbon in itself. You're mainly altering this particulate organic carbon fraction. So what sort of typical soil organic carbon levels do we have? Well, desert soils and degraded soils might have less than 0.5% organic carbon. You can have higher soil carbon in areas that support fire or wetland ecology and also human activity. You can have fire-derived soils that contain unweathered charcoal, can be up to 50% organic carbon. Then you can have peat soils and mollisols which can have organic carbon more than 50%, but they're exceptional. So in Australia, we have soil carbon levels that are typically a lot lower than many other places, and that's because, one, of climate, but two, a lot of broadacre agriculture is under cultivation. In general, most of our arable agricultural soils in Australia are about between 0.5 and 4%. 4 or 5% would be classed as high, and I'll talk about what you can do to go from low to high later on in the presentation. What does a high carbon soil look like? Well, this is a chernozem, it's not a vertisol, but a vertisol is a sort of a self-mulching black cracking clay. If you see a darker coloured soil, generally, not always, but generally, it can mean a higher organic carbon content. This picture was taken in northern Victoria. It's a lighter sandy soil. In Australia, it's called a calcareosol, but it's a sandy soil. It's been eroded. It hasn't got a lot of surface material. The soil organic carbon's about 0.6%, so very, very low. The second message that I'd make, that practices that improve soil organic matter are to be encouraged, regardless of whether or not someone enrolls in a soil carbon market, because there's a lot of benefits of improved soil organic matter. So a 1% gain in soil organic carbon represents about 133 tonnes of CO2 equivalents of emissions taken out of the atmosphere. So it has a big effect. Comes back to that 2,500 number that I talked about a few slides ago. A 1% gain in soil carbon is 144,000 litres per hectare. So it results in a significant gain in water. And assuming that that humus can release that water for use by plants, that can result in drought resilience. Then you can have improved chemistry, so it's got improved supply of essential nitrogen, phosphorus and potassium, can retain toxic nutrients. Physical benefits, so for example it improves the habitat for microbiota. It has biological benefits, can improve the biodiversity in the soil, and it's a source of carbon and nitrogen cycling in soils. So the collective impact of all of that, chemical, physical, biological, is often improved fertility, improved productivity, in some cases improved profitability. So you might say, well, what sort of interventions or practice changes can actually improve soil organic matter? Notice I'm talking about organic matter here, not organic carbon, and I'll talk about why that is shortly. You can retain crop stubble and make sure it's anchored, and so if you improve seasonal ground cover, you'll generally improve soil organic carbon. If you reduce excessive stocking rates, if you add more nutrients at strategic times of the year, if you reduce erosion, anything that you do to improve surface ground cover, for example, improve pasture species diversity so that they grow at different times of the year and or have deeper roots, then that can result in improved ground cover and therefore improved soil organic carbon. Remember, there's a trade-off between ground cover and soil moisture use, and so that may have implications depending on what sort of prevailing rainfall environment that you're in for subsequent growth. So there's a trade-off between ground cover and growth, but I guess it depends on whether you're aiming at pasture dry matter or soil organic carbon. You can convert from a cultivated annual crop to a perennial pasture. You can, if you're in a savanna area or a tropical area, you can burn early in the dry season, which is sort of cooler, instead of burning later in the dry season, which is more intense and hotter and drier and tends to increase carbon losses. Into row crops, you can sow crops between tree crops and vines. You can add organic amendments, for example, for spreading biochar to the soils. You can even think about clay delving or inversion, so bringing clay up and putting it on the surface and incorporating that into a non-wetting soil. Very touchy, and I'd encourage people to do a trial or a trial strip before they embark on a whole paddock in doing that. But if you've got a non-wetting or a restricted surface layer, that can have a benefit, and if that improves growth, you generally get an improvement in soil organic matter. You can add irrigation. In Tasmania and Australia is significant expansion in irrigated land use. If you change from a rain-fed area to an irrigated area, and you maintain that irrigation, soil organic carbon will go up because generally your productivity will go up, provided that you continue to irrigate. So we're doing a trial in northwestern Tasmania with biochar, feeding it to livestock. It's been touted as a win-win-win, so reduce enteric methane, so that's out of their mouth. It's undigestible, so it'll go through the animal and enrich their manure, and then the dung beetles carry the manure into the ground. And you can see the black tunnels into the ground, so they incorporate that carbon into the soil, and it's said to improve live weight gain. We haven't seen any signs of it as yet. We've only done one experiment, but there are other scientific studies that have shown that live weight gain improves, so it could be a win-win-win. To build soil organic carbon, we need to build soil organic matter. Now, in general, soil carbon can't be built up as an element, but it can be built up as a bundle. And across a range of surface soils, you tend to see a constant stoichiometry. And a stoichiometry is a ratio of carbon to nitrogen, phosphorus to sulfur. And it's this ratio here, 10,000 to 833 to 200 to 143. So what that means, if you want to improve carbon, you also have to improve nitrogen, phosphorus, potassium and sulfur. So if any of those nutrients are lacking, soil organic carbon sequestration will be constrained and can fall. You can't build up carbon in general by itself. That's if you're building it up by plant matter, unless you're talking about an organic amendment, but you can't really do that at a large scale. So improving soil nutrient balance and fertility can improve soil organic matter and carbon. And if you look at C to N ratios of a range of organic amendments, for example, poultry manure or humus, those that have a low C to N ratio, the plants really like, because there's more nitrogen for the microbes and easier to break down, and the plants say thanks very much. Whereas if you have a high C to N ratio, for example, sawdust or newspaper or even wheat stubble, like a C to N ratio of 80 or more, that can gobble up all the nitrogen and make it very difficult to grow, and that can cause what's called a mobilisation of nitrogen and therefore restrict growth, and it's generally not as good. So you want to aim for a low C to N ratio organic amendment. Now, the third point that I would make is that carbon markets attempt to decouple the effects of climate from those in management. Now, if you look at the long-term rainfall in Australia, the dark blue and the purple represent super high, and the orange and the yellow represent low, so 50 to 100 millimetres per year in the centre, and you get more and more rainfall towards the edges. Western Tasmania is probably amongst the highest, as well as up here near Cairns. Now, if you map long-term rainfall, this is between 1900 and 2005, so it's over 100 years, you actually see that soil carbon was lower in the middle, about 5 tonnes per hectare, and higher at the edges. So it's an amazing similar trend between soil carbon and long-term rainfall. So the question would then be, if you're if you're a landholder in Central Australia in the rangelands and you're attempting to improve soil organic carbon stocks, and you've got low soil carbon in the districts around you, you might question the extent to which that can be maintained for a minimum ERF or soil carbon policy. Whereas if you're near the edges and you're in a high rainfall area and your soil organic carbon is low relative to the carbon in the paddocks around you, well then you may have good potential for improving soil carbon, because it's going to come back to what it would have been in the long term. So soil organic carbon stocks have a high relationship with long-term rainfall. The fourth message that I'd make is that soil organic carbon is ephemeral. What do I mean by that? Well, this is a picture in northern Victoria, so this is a low carbon landscape. The carbon in that soil is about 0.6 or 0.7%. That's in northern Victoria in Australia. About 7 or 8 months later, that's the same shot, and that soil organic carbon's gone up to about 1.2% in the crop. It's about 1.3 or 1.4% under this native vegetation, which has never ever been cultivated. But it's ephemeral. It's only gone up and it's gone down because of the rainfall. In fact, this photo was taken in a La Nina, and when the La Nina finishes, the soil organic carbon in both the cropping area and the native biodiversity area will go down. The fourth message that I'd make is that soil organic carbon for permanence, which is what the carbon markets talk about, practice changes must also be permanent. Now, if you think about organic carbon, it can't be increased forever. It increases up to what's known an upper asymptote or an upper equilibrium. It's the same to a lower equilibrium if it's let go. In practice, soil organic carbon, if you're looking at organic carbon in percentage on the y-axis here, goes up and down. Droughts make it go down, high rainfall years make it go up, droughts make it go down, and so on. If you were to consistently add nutrients from some arbitrary beginning point, your soil organic carbon would go up, or if you cut out cultivation, or if you did any of those other things I talked about before. On the other hand, if you let it go, and you degraded the surface, and you degraded the soil, you overgrazed it, or you had erosion, or any of those factors, soil organic carbon would probably go down. On the other hand, you could start adding soil organic carbon and then stop, and then it would go down after some point. So if you've got to not just make a practice change, you've got to keep that practice change going. Now, if your soil organic carbon at some point in time is high, and then you propose enrolling in a soil carbon market to make money from a gain in soil carbon, and it's already high, you probably haven't got much to gain because you're up near the top. On the other hand, if you've degraded your soil and it's down near the bottom of that envelope, and if it's 0.4 or 0.5% organic carbon, well then you've got a large amount to gain if you make a practice change and sustain that practice change and keep it going up. And so you have a massive potential to gain in a soil carbon market. A farmer at Alice Springs said to me that soil carbon markets tend to make the good farmers bad and the bad farmers good. And what she meant by that is, if she had have built up her soil up to here and then decided she wanted to enrol in a soil carbon market, she probably wouldn't have much to gain. Whereas if she was a not so good farmer and overgrazed and degraded her soil and started off at the soil carbon market down here, she would have a lot to gain. So farmers are a little bit somewhat annoyed, at least the farmers that I've talked about what's called additionality, and I'll talk about that. And that comes back to my final message, which is divergent aspirations. So you've got individual livelihoods and farmer prosperity, and ultimately farms are businesses. Then you've got societal public good. So you've got mitigation of global warming. And so that's ultimately what the governments are aiming at. And so really what that comes down to is the issue of additionality. So additionality is an instrument within the soil carbon policy, or within a soil carbon instrument, that means that the rate of change of soil organic carbon relative to some baseline is greater than it would have been in the absence of a management change. So a lot of the people that I talk to are really concerned with additionality, the farmers that is, and the consultants, because it doesn't reward historical good management practice prior to enrolment in a carbon market. It makes the good farmers bad and the bad farmers good, as that I had on the previous slide. So if you're up near the top of that upper equilibrium, you haven't really got a lot to gain in terms of soil carbon market, so you probably wouldn't make much. In contrast, you've got a lot to lose. If you have a drought or a bushfire or erosion, you can easily go down again, or lack of good maintained management. But the government pays landholders based on additionality to incentivise them to adopt practices that actually improve soil organic carbon, because the government's goal, in contrast to the farmer's goal, main priority that is reduce global warming. So David Pennell in Western Australia had some good thoughts on this. On the y-axis we've got economic benefit, or cost per hectare. That dotted line is the cost of an intervention, and the bar, in this case, is the income from the intervention. Now, if you had some practice change and the farmer adopted that practice change, so it's a cost to the farmer. If the income resulting from that practice change, for example, sowing a different crop, if the income is less than the cost, the farmer generally doesn't adopt it because it's just an extra cost. It's the difference between the income and the cost. On the other hand, if you have the cost and then the government comes along with a carbon market payment and then the combined income plus the cost is more than the combined income from the practice change as well as the income from the government is more than the cost, well then you will have adoption, and that is additional because it wouldn't have happened in the absence of that carbon market payment. So that's what we want. On the other hand, you can have a non-additional case in which a farmer would have made the practice change anyway because the income from the practice change, for a new crop or a different type of tillage or whatever it is more than the cost. So the farmer would have made it anyway. And then you can have a non-additional case that the government comes along and says, oh, okay, you've made your practice change, we'll pay you for it as well. So what that is a perverse incentive because the government is paying people for something that would have happened anyway. So the government is making payments in attempt to mitigate global warming to instigate practice change. But if they're actually making payments for practices that would have changed anyway, they're not actually resulting in any mitigation of global warming. So David Pennell was of the view that we could abandon any system of offsets in soil carbon, and that would avoid all issues related to unfairness. The way I think about it is we probably could think about additionality, at least, in soil carbon markets in a different way. It could be sensible to pay people based on environmental stewardship. So you could pay them based on carbon stocks, that is a quantum, rather than carbon fluxes, that is a change in soil carbon. So that would remove the issue of additionality. So, for example, you might say, yeah, but soil carbon ranges widely, as you showed in that map of Australia before. Well, what you could do is you could come up with regional thresholds, and you could say, okay, farmer X, you've got a soil carbon that's more than the 75th percentile of where you are, and so I'm going to pay you. If your soil carbon falls below that threshold, which it probably would in a drought or for whatever reason, that payment cuts out. So what would happen then is that you would be paying people to maintain soil carbon stocks. You'd be paying people to maintain the carbon that they've built up historically, so that would remove the issue of additionality. And in fact, it would be paying people to keep carbon out of the soils. I mean, these environmental stewardship payments might be a lot less than the current carbon price. That's because you'd be paying probably a lot more. But in the end, you'd probably result in a lot more carbon out of the atmosphere because you're paying people based on a stock rather than a change. Now, a stock, I would argue, is much easier to measure than a flux because you're dealing with minute changes and you're dealing with large spatial variability. So it would avoid all issues associated with additionality because I would say absolute stocks are easier to measure than a change in stocks relative to some arbitrary baseline. So to come back to, and this is my final slide, to whether soil carbon markets are actually science or snake oil. Regardless of whether you're in a soil carbon market or not, practices that improve soil organic matter are to be encouraged. There's no doubt about that. At the continental scale, soil organic carbon stocks tend to follow long-term rainfall. The extent to which soil organic carbon can be improved depends on the timing of the baseline, your paddock history, the addition of nutrients, whether it's been cultivated, overgrazing, ground cover, soil texture, climate, all of these factors. Soil organic carbon can be gained, but it can be easily lost, for example, in drought. The costs of participation in soil carbon markets in Australia are currently high relative to carbon income. Financial returns from carbon markets vary quite widely, so talk to people who have done it before. Carbon credits that are sold from a farm business can't be claimed in a farm greenhouse gas emissions balance. So if you're aiming for a carbon neutral product, you can't claim those credits that you've sold, so that might conflict with your carbon neutral aspirations. Productivity benefits of soil organic matter often outweigh carbon income per se. That's at an Australian carbon credit price of $20 a tonne. If it went up to 200, it might be different. Some costs associated with acquiring ACCUs, at least in Australia, so that's a carbon credit, are tax deductible, but the proceeds of ACCUs are assessable income. So whether soil carbon markets are science or snake oil actually depends on the motivations and the values of the individual. Thanks very much for watching and hope to see you next time.